Hello, everybody. In this presentation, I will talk about location security under reference signal spoofing attacks. We will present threat model and bounds, and this is a work that I've been carrying out together with my colleagues in the framework of the European project Locus. The motivation behind this work is that location-based services are growing very fast lately, and the market is expected to grow from 20 to around 40 billion in the next few years. And in the recent years, many technologies have been used to provide location-based services according to the accuracy coverage trade-off. For example, the 5G, the recent 5G standard has been the first cellular standard targeting very high accuracy, even sub-meter, in a very large coverage area from indoor to outdoor. Regardless the specific technology that is used, the principle behind localization is common among these localization systems. We have a network of anchors, nodes in known position, the red circles in the figure, that want to localize a target, for example, a user equipment. This is made by communicating with the user equipment. This is the example of 5G localization, for example. There are specific positioning reference signals that are communicated with the user equipment, and then the information are sent to a location management function. The information that is collected at the user equipment or at the G0B is related to, for example, the time difference of arrival of the signal from different anchors, or maybe an angle of arrival, a direction of arrival. Some of the times it's a power measurement. In general, we have distance, power, angle measurements, which are jointly used together with prior information by a localization algorithm. In the 5G systems, the localization algorithm is run by the location management function. So basically, each of these communications provides a single value from each anchor. In the most trivial configuration with 3 anchors and 1 agent, we have a triangulation problem, like the one in the figure. From the estimate of the distance between each G0B and the user equipment, we draw a circumference which is centered in the G0B position. Looking even at this simple scheme, it's clear that we have multiple location security threats. Let's see an example. A first example can be the GNB impersonation. So we are changing the information about the G0B position. In other cases, we can alter the measurement process by interfering with the measurements that are collected or transmitted to the location management function. In some other cases, we can corrupt the control system, changing the information that we have about the measurements or the position of the anchor nodes. We can even have a rogue base station that communicates directly with the user equipment by impersonating another G0B. All these type of attacks have a common effect. At the end of the day, the anchor position is associated to an observable, which is the angle, distance, power, or timing measurements, an observable which is not representative of the claimed position. So we are altering the information about the user equipment. What's the effect in a simple triangulation problem as the one that we've seen before? For example, if I alter the measurement about the distance, I can make the system believe that the user equipment G0B distance is not this one, but a larger distance. This will ask for a triangulation with a larger anchor and a different position estimate. This is what happens if I alter the measurement process. If I impersonate the G0B, I can corrupt the control system, or I can impersonate the G0B and make the system believe that the G0B is in a different position. In this case, the measurement will be the same, but the center of the circumference will be changed. Again, the triangulation has to be made with different in a different configuration set. So the system will believe that the user equipment is in another position. In order to propose a formal threat model, we need to understand how the localization system works. In general, we first have a measurement model. We know how the measurement that we have, the angle, time, or distance, is related to the true position of the user and the position of the anchors. Here, PI is the position of the ith anchor. This way, if we know this function and we know the type of noise that affect the measurement process, we can draw a likelihood function, starting from the probability distribution of the measurement dependent on the true user equipment position and the true anchor position. In this way, we can think about a maximum likelihood estimation where the final position estimate of the user is given by the maximization of the product of this likelihood function from the different anchors. If we know the model correctly, in the end, we will have an unbiased estimation, meaning that this estimator P hat, the expected value as statistically is equivalent to the true position of the user equipment. Now, what happens, for example, when we alter the measurement process? If we alter the measurement process, it's like we are adding a bias, a delta I, to our measurement that we have made. This means that if we are unaware of this attack and we use the same model as in the general problem, we end up calculating the likelihood function for that anchor, including this bias. The final effect on the maximum likelihood estimator is that the estimator will be biased, meaning that its expected value is different than the true position of the user equipment. Something similar happens when we have a control system corruption or a G0 beam personification. In this case, the delta is not in the measurement, but it's in the position of the anchors. So basically, we calculate the likelihood with that wrong information about the anchor position. Again, the effect is a biased estimation. What we did as an initial study of this problem is to derive an error bound for localization under a spoofing attack, meaning that we want to understand what's the minimum error that we can get in the presence of an attack like a spoofing attack. We start from the fact that when we are in the presence of an unbiased estimation, the information inequality that comes from the Fisher information gives us a lower bound on the mean square error of the estimator. Basically, we have an inequality that gives us a lower bound on the expected value of the squared error of our position estimate, which depends on the Fisher information. This inequality, this lower bound, is valid only for unbiased estimator. In case of biased estimator, this lower bound changes, and therefore, in order to calculate a lower bound, we need to take into account mathematically the introduction of this bias. As an example case study, we considered range-based localization using RSSI, which is a very common method for localization. So basically, the observable from each angle is a range estimate that comes from a power measurement. Knowing the path loss law of the power, we give an estimate of the distance between each anchor and the agent. To provide some preliminary results, we considered a squared area where the anchors are uniformly distributed on a circumference. We consider a squared environment of 1 kilometer per side, and we perform range-based localization based on RSSI measurements. So each anchor performs a power measurement with respect to the agent, and in the end, we have an estimate of the distance for each anchor-agent communication. Then we consider that one or multiple anchors are spoofed, and we vary the bias that we can have for that measurement. Then we calculate the mean square error, varying the position of the agent uniformly in the squared area and considering a Monte Carlo simulation. In this example, we show the lower bound in dashed lines with respect to the mean squared error in solid lines. Red curve represent the case of a single spoofed anchor out of 4, while the blue curve represent the case with 2 spoofed anchors. What we vary here are delta, which is the extent of the bias introduced for each anchor, each spoofed anchor, and sigma, which is the measurement variance. So basically we can say when the value of the bias is above 100 meters, the effect of sigma is negligible, meaning that the value of the bias is the leading parameters for both the localization error and the localization error bound. In this other case, what we do is to increase the number of anchors that are available in this scenario. So instead of considering only 4 anchors, we increase the number of anchors, keeping the spoofed anchors to 1 or 2. As expected, increasing the number of anchors, we are basically increasing the number of reliable measurements that we have in the system. And when we go from 3 to 8 anchors, we compare the solid bars are the squared error in the absence of the spoofing, while the dashed bars are the error in the presence of the spoofing. So what we can see is that increasing the number of reliable anchors, we can reduce the final mean square error. However, even with 8 anchors and only a single spoofed anchor or 2 spoofed anchors, we cannot reach the same error that we get in this absence of the spoofing. So the effect of the spoofing can be mitigated with a greater number of anchors, but on the other side, when 2 anchors are spoofed, even 8 anchors are not sufficient to mitigate completely the effect of the spoofing. These are only preliminary results. What we wanted to provide here is a formal reference model designed to abstract a variety of localization spoofing attack. And our model may become a convenient formal benchmark for location security assessment. So the idea here is that starting from this, we can start thinking about the algorithms for the detection of location security attack and for the mitigation of location security attack. And for example, we can compare the error in the presence of a mitigation technique with the error bound that we get in the presence of a spoofing attack. For further references about localization and location-based analytics in 5G and beyond, where we are also working on location security, you can refer to our European project Locus. Thank you for your attention.